All right, let's go over the solutions to the exam. The first question, part A, asked about the rate of change of the area of a circle at a certain time. And I'm sorry I'm a little bit slow here because I'm having a little trouble with one of my apps here. And so that says at the instant the first circle has a radius of 9 centimeters, the radius is increasing at 3/2 centimeters per second. Find the rate at which the area of the circle is changing at that instant and indicate units of measure. So this is a pretty straightforward problem here. We have to remember the area of a circle, pi r squared. We have to differentiate with respect to t. And so when we do that, we get 2 pi r times dr over dt, or r prime if you prefer that notation. That's fine. They told us that dr over dt is, since it's increasing here, is positive 3/2. And they also told us that this is happening when the radius is 9. And so dA over dt is just 2 pi times 9 times 3/2. And if we do a little bit of arithmetic there, you get 27 pi. And then it does say indicate units of measure. And so some of us got this wrong because we weren't paying really close attention. And you have to remember that you got to look at this ratio over here. On top we have area, and on the bottom we have time. And so the area was in centimeters, so or at least the units of measurement were in centimeters. And so area is going to be measured in centimeters squared, and the time is going to be, I don't remember now. So let me go back and take a quick look. It was per second. And so this is going to be centimeters squared per second. So look at the area in that ratio when you're looking to answer a question like that. Now for part B, it says the radius of the first circle is modeled by this function w between 0 and 6 inclusive, where w of t is measured in centimeters. So this is the radius. This is not the rate of change of the radius. This is the radius itself. And you can again see that by looking at units, and they give you some sort of indication of what's happening here. And the units say that the answer is, or the w is measured in centimeters. So that's a length. It's not a rate. It's not centimeters per second or something like that. And we want to figure out at what time t is the radius of the circle increasing at a rate of 3 centimeters per second. So we need a rate function for the radius. So we're going to have to take the derivative of w and then figure out when that's going to be equal to 3 centimeters per second. So w prime, of course, the derivative of 12 is 0. Constant multiple rule for this 12. Exponential is its own derivative, but we have to apply the chain rule. So we have to multiply by the derivative of the inner function. And then the negatives cancel, of course, and half of 12 is 6. So this is works to be 6e to the negative 0.5 t. And we want to know when that is equal to 3. So we set that equal to 3, and then we do some arithmetic here. So, of course, we're going to divide by 6. Whoops, let me write this properly here. And then we're going to need the natural log function. So we get the natural log of 1/2 is going to be equal to negative 0.5 t. And then t is going to be natural log of 1/2 divided by negative 0.5. Or dividing by half is the same as multiplying by 2, negative 2, natural log of 1/2. Now, if you're not thinking carefully about this, you might be slightly confused, and they may have been trying to confuse you when they wrote this. You might think, well, how am I getting negative time? Well, you're not. The natural log of 1/2 is going to be a negative quantity itself, so the negative times negative gets a positive. One way you could see another form of this is to use one of our log exponent properties. Remember, if I take log, it's any base, but I'm going to use just the natural log for this. The natural log of a to the power of n is n times the natural log of a. So I can use that negative and bring it up as an exponent. So this becomes 2 times the natural log of 1/2 raised to the power of negative 1. But that's just 2 natural log of 2, or if you want, you can bring that 2 in also and just have the natural log of 4 as the answer. All those are equivalent. Any one of those would be counted as correct, so you don't have to worry about rewriting any of them. In fact, you could stop way back here at the beginning. Many of you did. It's correct. and that's good enough. For part C, this is a model for the radius of the second circle. This is given by a function f for t between 0 and 6, where f of t is measured in centimeters, t is in seconds. This is the rate of change of the radius of the second circle is given by this function f prime of t, and this is based on the model. How many centimeters does the radius of the circle increase between 0 and 3? So since we're just looking for an increase, we're looking for a change in the radius, or the net change in the radius. So we just got to write an integral for this. And so we just write the integral from 0 to 3 of t squared minus 4t plus 4, then we'll get our net change in and we'll get our answer. So for a question like this, they give you a point for the integral, they give you a point for the antiderivative, and they give you a point for the final answer. So not too challenging to come across these points. We just got to make sure we don't make any silly mistakes along the way. And so when I plug in the 3 squared, see, there's a silly mistake. I said let's not make any silly mistakes, and I almost did. It should be 3 cubed. 3 cubed is 27, and a third of that is 9. 3 squared is 9 times 2, negative 2, or minus 18. And then plug in 3 here, we're going to get 12. Plug in 0, we're going to get 0 for all of those. And then 9 and 12 is 21, minus 18 is 3. And so there's a change of 3 centimeters in the radius between 0 and 3. So it's the answer to that part. Okay, for the second question, we had this graph, and then we have this function f, which is 3x plus the integral from 0 to x of g of t dt. And for part A, we want to find f of 7 and f prime of 7. Let me switch screens slightly here. So for f of 7, we're going to, of course, plug in 7 for x. So we're going to get 3 times 7, which is 21, plus the integral from 0 to 7 of g of t dt. So let's go to the graph and kind of see what we have to do for that. So from 0 to 7, well, we're going to have the area under the curve here, or below the x-axis, between the curve and the x-axis. That's negative, and many of you forgot to make that part negative when you're working this out. And then from 6 to 7, it's just this positive little area here, just 3. So we're going to have to find the area of the semicircle, make it negative, and then add to it the area of that that 3 square unit rectangular area. Let's talk about the circle for a little bit. Well, we have a radius of 3, and so the area of this part over here, not going to make it negative yet. I'll make it negative down here, but so it's 1/2, because the semicircle pi, the radius is 3, and so we get this right here. So we're going to get 9 pi over 2, and so f of 7 is going to be 21 plus negative 9 pi over 2 plus 3. Yeah, so this is going to be 24 minus 9 pi over 2. And that's going to be the area for, rather, it's going to be f of 7. Now to figure out f prime of 7, we need f prime of x first. Of course, it's going to be 3 plus g of x. So f prime of 7 is going to be 3 plus g of 7. And let's go back and look at g of 7 really quickly. G of 7 is 3. It's right over here. Okay, so let's go plug in 3 for g of 7. And so f prime of 7 is 6. Just as a reminder, so f of 7 was 24 minus 9 pi over 2. That was part A. All right, for part B, it says find the value of x in the closed interval -4, 3, at which f attains its maximum value. Justify your answers. Now we're looking for an absolute max here. We're not looking for a local or relative max because we'd have to ask for those specifically. So some of you misread the question or misunderstood the question and looked for relative extrema and not absolute extrema here. So we're looking for the absolute maximum, the x-coordinate at which the maximum value occurs. All right, so let's go back for a moment to this screen. So there's a couple different ways that we could think about this, and we'll go through a couple of them. So to figure out, since this is a closed interval, we'd want to use the closed interval method. So we take the derivative, which we have up here, and we would want to set it equal to 0, find out where it's undefined. So it equals 0 when g of x is equal to -3. And if we go back to the graph really quickly, g of x is equal to -3 at 3, which happens to be an endpoint. So this is at x equals 3. Now, going back to the graph really quickly, of course, we always want to find out where the derivative is undefined. Now, some of you misunderstood this here. The derivative is g. Well, it's 3 plus g, but nonetheless, there's no place on here where g is undefined. G is defined everywhere between as it says right here in the open, g is defined on the closed interval -4, 8. So there's no place where g is undefined. So f prime is not going to be undefined because it's just 3 plus g, okay? So there's only one place where f prime is going to equal 0, and that's at 3. It's an endpoint. So really all we have to do is test the endpoints, compare the value of the endpoints, and see which one's the biggest, and that will give us our x-coordinate here. So we go back and find f of 3 and f of -4 and see which one's biggest. Now, some of you did that, and some of you did it well, and that's certainly a way you can do it. But I'm not gonna continue that argument right here. Just do the mathematics. You're gonna find out that this one is gonna give us the max here, and so the max is gonna occur at 3. But notice something here that since f prime of x is 3 plus g, this is going to be greater than or equal to 0 on the entire interval from -4 to 3. And the only time it actually equals 0 is at 3, okay? Which means that f is always increasing on -4, 3. And if f is always increasing on -4, 3, therefore f has its max at x equals 3. If a function's always increasing, then it's going to take its maximum value at the right-hand endpoint. It's going to take its minimum value at the left-hand endpoint, okay? And if a function's always decreasing, then it's going to take its max at its left-hand endpoint and its minimum at its right-hand endpoint. So this is a way that you could have gotten the answer. You certainly could have done the closed interval method over here, which I'm not going to complete for you. You could do it. But I'm just trying to show you that this is an alternate way of thinking about it. In fact, this is what they had in the solution over here. I might have done the closed interval method and gotten the points that way, but I'm sharing with you another way of thinking about it that was in the solution guide. Now for part C, we have to find a couple of limits, both of g prime, and we're looking from the left of 0 and to the right of 0, as x approaches 0 from the left and from the right. A lot of you just jump to an immediate conclusion, and it was wrong, at least in part, and you kind of got lucky on half of it. And I'm not sure that they would give you it the way I did, but I'm hoping. So what was the jump to conclusion? A lot of you saw that there's a sharp turn right here, and you said, well, g prime doesn't exist, and so those limits don't exist. And that in general is not true, okay? Now, g prime doesn't exist, function's not differentiable there, but we're looking from the left and from the right, and the left-hand and right-hand limits can exist. They're just not gonna be equal to each other because of the sharp turn, okay? That doesn't mean they both have to exist, but they're not going to exist necessarily. They're not going to not exist necessarily just because the g prime doesn't exist at that point. What does g prime tell us about the graph? It's the slope of the tangent line. So on this side of the graph, the slope's constant. what's the slope on this side over here? Well, it's the slope of this line, and the slope of this line is just 1/2. I'm sorry, negative 1/2. Now, over here, we'd have to look at the slope of the tangent line as we move along the curve here. What's happening to this, okay? As we move along the curve in this direction here, the tangent line is getting steeper, okay? And in fact, at the edge of the circle over here at this far side, the tangent line would be vertical, which means that there is no slope because a vertical line doesn't have a slope. So the limit does not exist. Now, you could put negative infinity because if you look at all the slopes on the side, the slopes are negative and getting steeper. Negative infinity would be an acceptable answer. In the solution guide, they only put does not exist, but I know they would have to give you credit for negative infinity. Um, from this side, from the left, it's going to be negative 1/2, and from the right, just you can say as they did, does not exist. Or you can put negative infinity. But if you put positive infinity, unfortunately, and a couple of you did that, it's not correct because it's the wrong infinity, and they shouldn't give you credit for that. It's one of those things that you have the right concept, you're slightly off. It's like just like a miscalculation. If you have a miscalculation, even though everything else was correct before it, you're still going to be wrong. So be careful with that. All right, so in letter D, we have to evaluate this limit. 9 times out of 10, ladies and gentlemen, if they're going to have you do a limit like this on an AP exam in the free response section, you're going to be doing L'Hopital's rule or the squeeze theorem, but probably L'Hopital's rule because that's just the way they tend to test. Okay, so we have to see what's going on here. And this is a L'Hopital's rule problem, so let's figure out how this works out. So if I do direct substitution, I got to figure out what f of negative 2 is. And I didn't work that out ahead of time, but I know it's going to be negative 7 because um, I know that this is going to go to 0 over 0. And you need to show that. The denominator is obviously 0. Let me maybe help a little bit with f of negative 2. So get rid of some of this stuff here. So f of negative 2 was going to be 3 times negative 2 plus the integral from 0 to negative 2 of g of t dt. But this is going to be, this is of course negative 6 minus the integral from negative 2 to 0 of g of t dt when I flip those upper and lower limits of integration. And from negative 2 to 0, we're talking about this right here. This is just a triangle, which is going to be half the base. The base is 2. The height is 1, so that's going to be 1. So this is negative 6 minus 1, or just negative 7. And so then we get our 0 over 0. And again, you got to put 0 over 0. If you jump right into L'Hopital's rule without showing you got that 0 over 0, or if another example had to be infinity over infinity or some combination of an infinity over another infinity, you need to show that because they're going to give you credit for recognizing the need to use L'Hopital's rule. Then they're going to give you a point for using L'Hopital's rule. Then they're going to give you a point for the final answer. That's typically how it goes. So using L'Hopital's rule here, get x to is expressed as negative 2. We're going to get f prime of x over 3e to the 3x plus 6. And so we're going to get f prime of negative 2, which again, I didn't work any of this stuff out ahead of time, but if I plug in negative 2 here, that comes out to be just 3 on the bottom. F prime of negative 2 is 3 plus g of negative 2, and that's going to be g of negative 2 is 1. So it's 3 plus 1 over 3, or 4/3 as the final answer. On this practice exam, we did some good stuff. It was a lot of review, and that was on purpose because we have to know this stuff as well. So it's time to learn from your mistakes, rekindle those thoughts, those memories that you once of the skills you were once really good at and maybe not so good anymore because just a little bit out of practice. You can get it back. Okay, so now's the time to put some effort into it to really understand what you were thinking versus what you should have been thinking. Let's clear up the mistakes. Let's start doing higher quality work that we're certainly capable of, and let's perform better on the next one. Go study.